Morning students, today we are going to learn a new theorem, that is maximum power transfer theorem. In last class we have seen few theorems like superposition theorem, star delta conversion theorem, Thevenin's theorem, Norton's theorem. At the same time, KCL and KVL terms and regulations and Ohm's law. By using these all network theorems, we have simplified a complex network into our convenient way to know the response in a particular element. Similarly, here we are going to find that how the power is transmitted from source to load, at what is the value of the internal resistance value and load resistance value. If these two are matches, what will happen? At that condition, what is the voltage across the terminals? So, this all will learn in this session. Okay. So, generally this maximum power transfer theorem is used in electronics circuits where the power transfer is maximum. Okay. So, let us see one by one. So, this topic is regarding to EE 302C and network theorem, and today we are going to learn maximum power transfer theorem. So, in last class we have seen that statement of Norton's theorem, explanation of Norton's theorem and application of Norton's theorem to find some responses in a given circuit. After that, today our object, on completion of this talk period, you would be able to know statement of maximum power transfer theorem, derive the expression for maximum power transfer to the low terminals, what is the condition, and apply this maximum power transfer theorem to a given networks to solve the problem, to know how the maximum power is transmitted from source to load. Now, what is the main idea of this theorem? So, maximum power transfer theorem, generally it is applied for DC networks. Sometimes we can apply it for AC networks also. In DC networks, generally we know that in our electrical engineering, the load elements are resistance, inductance and capacitances. These are the three different loads. As you know that resistance always consumes power from the supply in the form of I square R, whereas inductive load consumes and returns same energy. In case of the AC, during the positive off cycle, it will take the power, and during the immediate negative off cycle, it will take the whatever the energy is taken is given out to the load. Okay, what do you mean by the maximum power transfer theorem? As we know that it is applied to the DC networks as well as the AC networks. In case of the DC networks, the impedance we are taking as a resistance only. No inductive is placed in this case DC, because the in inductance means omega L. Omega L is equal to 2 pi FL. So, F is the frequency. In DC, the frequency is 0. So, here we considered only ohmic value is equal to resistance in case of DC. For if your same theorem is applied for the AC networks, that in that case we are going to consider the impedance. The impedance Z is equal to R plus J of XL. So XL is based on the frequency. Okay. So let us see in case of the DC circuits. So what do you mean by the definition of maximum power transfer theorem? A resistive load will abstract maximum power from a network when the load resistance is equal to the resistance of the network as viewed from the output terminals, with all sources of EMFs removed, leaving behind their internal resistances. So this is the definition of DC, maximum power transfer theorem in case of DC. So what is that one? Don't panic. So we will see one by one. Okay. Now, so this is a maximum power transfer theorem we are going to do in our laboratory. This is a one trainer board in our electrical circuits laboratory. Okay. So this is a very easy and you are going to enjoy performing the experiments. Okay. So this is a one trainer board. This is essential for you also. And so what we have seen, so before going to the maximum power transfer theorem, how the power is transferred from the source to load center. As you know that power equation in a resistive network. So for example, if you are taking the one small circuit, here what is the circuit? So here is a one DC supply is given. Okay. Now we can take one. Okay. Now one circuit is this is a DC circuit. Okay. Now this is a switch and this here connected the one resistance and connected to the here. Now this is a resistance. Now one switch is closed. The current will flows through this network. Okay. The current will flows I. This is a voltage. Now as per Ohm's law, we know that what is the current? Current is equal to I is equal to V by R. Okay. After knowing the I, so the power I required, power can be written as power transmitted from the source to load, that is a P is equal, we can write it, what is the voltage, what is the current in the circuit, or we can write it that is equal I square R. Same thing we can write it, so V square by R. So that means we can write the equation in three forms. So P is equal to VI watts and I square R and V square by R. As per terms given, we are going to calculate what is the power of a network. How much power taken by the resistance. Okay, this is the basic idea already you known in previous classes. Now this is the, you can see, in a resistor the power will be consumed in the form of heat energy. So what we have seen here, the circuit, so we are connected one lamp. For example, take the resistance is the one lamp. What is consistent? It has the resistance. Okay, R. So whatever if you are closer this one, your voltage applied, the current will flows. The current which is flowing through the resistive materials and comes to the 0. Then here the resistance presents. So heat is developed. H is equal to I square or T by J. Here terms already you know, very familiar. I is the current flowing through the circuit. R is the resistance of the bulb in incandescent lamp. And T is the time, how much time you are going to performing experiment. J is the Joule constant 4.2. So based on this one, the heat will develops. In pure resistance, whenever the current is passing through the resistive material, it establishes, it produces the heat energy. That heat is dependent upon the current, square of the current, resistance of the element and time and the Joule constant. Joule constant anyway it is a constant. Only is dependent upon the time as well as the current in a time based. Okay, so that is in a resistor the power will be consumed in the form of heat energy. So here definition once again we are going to see it. So this can be applied for the DC networks in this case. Now what is the definition? A resistance, here you can see one, I will draw the one figure. For example, here is one source is connected here, and we know that every source having its own internal resistance, and it is connected to the one network. We can say this is a RL, load resistance. This is source. When a resistive load will abstract a maximum power, it will draw the maximum power when from a network, when load resistance, here the load resistance is the RL, that is called this one. Load resistance equal to the resistance of the network. So here is small r, or sometimes there is another resistance also here present in the network. So that means here this resistance, this resistance, this resistance combination. So if you are adding this resistance, for example, that is equal to, we can take the R internal resistance. If RL equal to load resistance equal to internal resistance RI, as viewed from here the output terminals, we are seeing the output from these terminals. Okay, with all the sources EMFs removed, leaving the behind their internal. So as we know that. So here what is happened? When this internal resistance whenever equal to this load resistance value, at that condition the maximum power is transferred from source to load. This is the definition of this thing. Okay, so at that condition, what are the conditions? Oh, we are going to get the only 50% of efficiency in that condition only. Power is transferred maximum, but efficiency of the system only 50%. At that condition, the voltage at the terminals only V by 2, that is half of the voltage appear at this terminal. These are the few salient points in case of the DC. Okay, so what is saying? A resistance, here a resistive load will abstract maximum power from a network when the load resistance equal to resistance of the network as viewed from the output terminals, with all sources of EMF removed, leaving behind their internal resistance. That for the R Thevenin is nothing but. Okay, so this is the definition of this. So let us see in a circuit way. You can see here what you are seeing. This is a DC network, and this is the X and Y is the load terminal. This is the one complex circuit, for example. So this is converted into simple Thevenin's equivalent circuit. In figure A, you can observe one DC network, and it is connected to the one variable resistance. It is connected across the X and Y terminals. If it is connected X and Y terminals with the RL load, the current is flowing from the DC source to load through I current. If the load current is varied such a way that if this load current is equal to the internal resistance of the circuit, at that condition the maximum power transferred from source to load. So here you can see generally this maximum power transfer theorem is mainly applicable to in communication system, this electronic system. So because what will happen whenever this RI internal resistance is equal to RL, that means it is a variable. It is by varying at what stage it is tuned and equal to RI. At that condition we will draw the maximum current, maximum power. At that condition, what is happened? The voltage across the terminal is a V by 2. Is, for example, this is a voltage, we half of the voltage appear here. At the same time, the efficiency also of the system is the 50%. Why should lose the 50% losses in case of the power transmission system in our electrical? So it is only for not used in our transmission system. It is applicable for the only in case of the communication and electronic system where power is required, the maximum losses is considered as negligible. That is, a loss cannot be bothered. 50% losses, no problem. I want the maximum power. So that's why you require the maximum audio output. So with the signal input, so we are amplifying the maximum to a loudspeaker. At that condition, we can use this is the application of maximum power transfer theorem. Okay, we will see later how it is what is the condition. Okay, now let us see simple circuit. What is this in the circuit? What you have seen? So here the DC network is nothing but consists of the voltage source and one internal resistance. And is a coupled transformer. From this one is given to the one load. One load resistance, you can see here is a 8 ohms, for example, resistor. You can observe it is a resistance, there is a 8 ohms, 16 ohms and 4 ohms. That resistance should be connected to the amplifier. So this is a communication purpose. Let us take the one simple circuit in our electrical circuits and analysis what is the condition for transfer of maximum power condition. Okay, let us do. Now, here you can take the one simple circuit. What is this circuit? Here is the voltage source represented by E and it has an internal resistance small r, and here is one R1 is connected, one resistance, and here is the R2 is connected. Terminal A and terminal B terminal, here we connected the one load resistance. Okay, this is a simple circuit. A voltage source and resistance and is connected. Okay, now let us calculate what is the condition. Now here let the RL is the load resistance in ohms, the small r is the internal resistance of the battery, the RA is the total resistance of the circuit as seen from the load terminals A and B. Now it is a remove it and see from this one you are going to see what is here going to appear, the internal resistance. The internal resistance, whatever the voltage source, simply short it, and what is the R, indicate here. So that means your internal resistance small r, and this is the R1 and this is the R2 connected across this terminal. Okay, so this is one thing you now. So where Ri is the internal resistance is equal to, how you are going to write it? Let us write this one, same equation, and this is a source is given, here R1 is given, R2 is given, and internal resistance here given, and this is the terminal you are going to calculate. Okay, this is a A, this is a B. This small r, this is a R1, this is a R2. So RL is here connected, we taken out, and this is a plus minus voltage source. Now by seeing from AB, what is the total internal resistance? As you know that voltage source is shorted. Now what is happened? Now this is a small r and small r1 is connected here. Okay, now R2 is connected here. This is a this is a B. Now by seeing here, what is happened? R2, R1 and small r. Now equivalent resistance is equal to, that is you can say the Ri. Can I write Ri is equal to R1 and R is in series. Okay, can I write it? This is equal to here, I cannot write it, this one, and this terminal, this is A, this terminal is B. Okay, this is the R2, this is the small r plus R1. Now, what is the equivalent resistance now? This is equal, we can write it, that resistance is equal to, and both are connected in parallel. Then we can R1 plus R small r, we can say this is only this one. Okay, you can take it. Then what is the R plus R1 into R2 by, here all are connected, small r plus R1 plus, this is called small r1 plus R2. This is, we can say this is the R internal resistance. Okay, so this is the resistance by seeing terminals from A to B. That this is nothing but R Thevenins or Nortons. We have seen already previously. Okay, so R Thevenins or Nortons is equal to the Ri internal resistance. This internal resistance, if equal to the R load resistance, then we can say that the maximum power transferred from source to load. This is the condition. Okay, same we are seeing this here also. So how we are going to get it? So now we have seen R1, R2 in parallel with these two. Then, so RL will abstract maximum power from the network when the load resistance equal to the internal resistance of the network. Okay, so how we are going to tell, sir, this one? What is the proof? What is the proof? How we are going to tell that maximum power, how can it will transfer from source to load when the condition is this one? Let us prove it. Okay, now prove it. Here we take the same circuit. Okay, now what is the circuit? Here proof. Then draw the diagram. Same, this is the one resistance, and you connect the one resistance internal Ri and connect to the RL. So V. Okay, so this is you can say this is E voltage source. This is Ri internal equivalent. Now we have previously we have seen derived that thing. Okay, so Ri. Next, this is the RL. Now, based on this circuit, the current, what is the current in this circuit? What is the current now? So, I want to know the current I. I can write it from this circuit. I current is I is equal to voltage by equivalent resistance. Now, what is the equivalent resistance? RL and Ri connected in series. That is equal to Ri plus RL connected in series. That is the current. Now, I want to the power. Power is equal to P load is equal, we can write it. So, V into I, IL, or we can write it I square RL, we can write it V square RL. Okay, that is a voltage across the AB terminal here. I through the element. So, here the PL can write it as a load, power load is equal to I square R L load. So, what is the I? Substitute this value in this one. Okay, then you are going to get it. So, what is the value? E I square means this is the square of this value. So, E by Ri plus RL whole square into RL. This is the equation, that is called PL. Now, for PL, load power max to be maximum, differentiate this PL with respect to the load resistance, then equal to the 0. As we know that whether we are going to find the maximum or minimum, we are differentiating that thing with equal to the 0. Similarly, you have to differentiate it. Okay. So, let us, so this can be seen in the animation now, you can see it. Same proof, the circuit current is equal, I is equal to E by RL by RI, and power consumed by load is PL, and PL is equal to I square RL, and where I is equal to say E by RL plus RI whole square into RL. Now, for maximum power load to be maximum, that is a dPL by DI. So, we are going to this one. So, manufactured PL. So, differentiate this thing and equal to the 0. So, we are going to this value. So, what will happen? You can see. Okay. Now in this case, what we have seen in previously? So, we have seen that equation. What is the PL? Okay, we will show here. One second. Now we will see here only. Okay. Now, previously what we have seen. So, once again I am going to write it. So, this is a one circuit. Okay. The equivalent resistance is Ri, internal resistance. Now, it is connected to load resistance. This is called RL. Okay. And this is a A, this is a B, and this is the energy source E. Now, I want to know that what is the power consumed here, PL, power across this one, P load. As we know that I is equal to, as per Ohm's law, V by equivalent resistance, okay, total resistance, that is equal to V is equal to E by RT is equal to Ri plus RL is connected in series. So, Ri internal resistance plus load resistance. This is the equation. Now, P load is equal to I square RL. Okay. What is I square? Is E by Ri plus RL. Okay. So, this is the total whole square into RL. Now, this is a PL. For maximum value, I want to differentiate equal to this one. So, dPL by dRL. Okay. dPL by R is equal to 0. Now, what is this equation? So, here similarly we are going to write it d by dL dRL is equal to equation right here. Simple, E square by Ri plus RL whole square, okay, into RL. This is a equation equal to 0. Okay, the differentiate this equation with respect to the load resistance. So, what has happened here? Now, so this equation now it becomes to, so it's simple equation, you know that. So, here E square into RL, RL is a 1, you are going to get Ri plus RL whole square minus E square RL, and then, so what has happened? This will come to the into 2 into, so we are going to get it, okay, that is called RL Ri plus RL 1 divided by Ri plus RL whole to the power of square, that is square is equal to, we are going to the 4. Just dV by the equation. So, differentiation of dV by du by dV. Okay, that you know that thing, you are very familiar. Now, equal to 0 this value. Now, you can convert this one, and E and here is also same thing. Just simplify that thing. Okay, so after that simplification, what you are going to get here, Ri plus RL whole square, then here is the 2 into RL into this is called Ri plus RL equal to 0. Okay, then what will happen? So this one and this one will get cancelled. Then you go to the that side, Ri plus RL is equal to RL. Or you can come this here. Then what is happening? Now this is equal to Ri internal is equal to, is going that one, so simply RL. So that means a variable load resistance equal to internal resistance. At that condition, we are going to get the maximum power transferred from source to load. This is, and it is proved. Okay, so dear students, this is a mathematical equation. You know the very well how to differentiate this thing. Okay, now it is proved that the internal resistance of the circuit is equal to the load resistance. At that condition, the power is transferred from the source to load is maximum. Okay, so this we proved. Now you can see once again in the animation. Okay, now you can see, so differentiate the equation 1 and simplifying we are going to get, so this is the equation, or we are going to get this value. Just we prove it. Okay, so hence the maximum power is E square by 4L. How we are going to get that one? So we will see. Okay, so that is the maximum power is equal to justly substituting substituting this value in power equation. So where power already we are seeing, PL is equal to, so what is the value? E square by something, E square, what we have written previous case, that is what is the E square RL by RL plus Ri whole square. Okay, that is the value. Now substitute this of the same, Ri and RL is equal. Then we are going to E square into RL by RL plus RL, 2RL. Okay, 2RL whole square. So by simplifying here, what we are going to get? So here that value, so we are going to get, what is the value? So here this here is a 4, this is a 4, it will become a 4 RL square. This one, this will get cancelled. Okay, then what we are going to get? So E square by 4 RL is the equation for maximum power transmission. Okay, so that is the we are going to see here. So that is hence the maximum power is equal E square by 4 RL. That is the value. If you know the E value, if you know the RL value, you substitute, that is the power at that condition. Okay. Now, so this is the equation we derived. So everything is same. Now you can see this application used in electronics. So here the maximum power transmission, the voltage across the load is of the open circuit voltage at the terminal AB. That means here, so for example, whatever the voltage is connected here, E and A and B, when maximum power transmitted here at that condition, this is E by 2 only at this condition. That is the meaning of this one. At the same time, the overall efficiency of the network supplying the maximum power to the load terminal is only 50%. At that condition, the efficiency is 50%. That means 50% is a wastage. Half of the power is wasted in the network in the form of a heat energy. So we not preferred in case of our electrical system, it is preferred for in communication. That's why it is used for the audio amplifiers. You can see that. So here the efficiency is only 50%. Load resistance increase upon load resistance increase, the low resistance varied, when load resistance is equal to the Ri internal resistance, we are going to the maximum here. That is a 50% maximum transfer at that condition. If further increases the load resistance, automatically decreases to the losses and power. So go on increasing at the maximum and once again decreasing if load resistance varies. Okay. Now the overall efficiency of the network supplying the maximum power to the load terminal is 50% only. The half of the power is wasted in the network itself. So what is the application? This is the one application. What is the application? The maximum power transfer theorem. The application is the application of this theorem to the power transmission and distribution network is limited, because in their case the goal is high efficiency. So where we require the high efficiency, we cannot prefer this the maximum power transmission theorem in transmission distribution system of in power system. This theorem is applicable only widely used in communication networks, because in their cases the goal is either to receive or transmit maximum power only, not depend upon the efficiency. That's why it is very advisable to prefer in case of the communication system. Okay, so this is the one thing. Now coming to the what are the salient points. If we consider the efficiency as the fraction of power dissolved through the load or to the power extended with the other sources, then we are going to write it that V Thevenin's, then it is simply complete the efficiency as. So here efficiency is equal to phi maximum by P is equal to 50% only. So here this is only 50% efficiency, where the maximum power P max already we have seen, that is called V square by 40H. We derived this equation also. Power we derived the E square by 4 RL, that is equal, here we written as a 40H. Thevenin's, we are equivalent to Thevenin's. And the power supplied P is equal to, so we can see this is the power supplied. The power supplied is equal to, so that is a half of that 50% of only power, that is called V square TH by RTH. Okay, so that means here we are assumed this one, so the resistance and we taken this R Thevenin's and the V Thevenin's. So this is we are going to transmit the power, this is equal RL. At that condition we are going to do this all calculations. Okay, so here the efficiency is only 50% when the highest power transfer is attained, although reaches 100% as a RL load resistance reaches infinity. If resistance infinity, we are going to get the 100% of efficiency, but it is not practicable, while the whole power stays tend to 0. Okay, so this is the one thing you have to remember. Okay, so you may have some confusion. What is the power transmission theorem? So nothing but don't worry. The power transmission theorem is equal to simple what we have seen previously definition. Just you remember that a resistive load will abstract the maximum power from a network when the load resistance equal to the resistance of the network as viewed from the output terminals. Okay, so that is a definition of this thing. Now based on this one, what is the condition? So condition is when internal resistance is equal to the load resistance, the maximum power transmitted from the source to load. At that condition, we are going to get the efficiency point of view 50% and voltage point of view only half of the voltage with open circuit voltage comparing. Okay, then so we are going to apply this type of the networks in communication system. Telecommunication, it is the very preferable, not advisable widely in our transmission distribution system and power system. Okay, so these are the things you have to observe. Now let us do the one problem. So calculation of V Thevenin's is given. So maximum power, how the maximum power is transmitted, what is the wattage we are going to calculate. For example, you take the one problem. Now So, we do the one problem. So, what is asking? Calculate the V Thevenin's for a given circuit. What is given here? Here is given the one current source and connected to the one resistance, and he is connected to the another resistance, and here connected the another resistance. Here is taken the this one. For example, this is a A, this is a B. Okay, so current sources are 10 amps, 10 ampere current source. Now this is a 3 ohms, and this is a 3 ohms, and here is a 2 ohms. Now I want to know that what is the PL maximum, PL max, how much maximum current will takes, how many watts is required. Okay, how much power is transmitted to the AB terminals. So we are going to calculate it. For this purpose, so we know that what is the formula? The PL is equal to, we know the formula already we have seen, that is equal to, what is the formula? That is equal to V E square or V Thevenin's. We are going to with Thevenin's divided by, so 4 into R Thevenin's. So V Thevenin's we are going to find it, R Thevenin's we are going to find it, then we are going to get the P maximum. Okay, that purpose what to do? Simply calculate the what is the this one. So you can apply Norton's theorem or Thevenin's theorem. You are going to find that is the what is the V value or R value. Okay, what is the R Thevenin's? By seeing here, you are going to get it. So R Thevenin's we are going to simple. This is the current circuit. Open it because there is no internal resistance is given. Here is 3 ohms resistance. A 3 ohms resistance connected here, and here is a 3 ohms. This is connected here. Okay, this is a 2. This is a 3. This is a 3. We are going to calculate so A and B terminals by seeing this one, because this is open. So I want the only resistance of this one only. So 2 plus 3, that is equal R Thevenin's is equal to how much? 2 plus 3 is connected series, 5 ohms. That is enough. Already we have done so many problems. Okay. Now I want to know that V Thevenin's. I want to know the first case is over. Second case I want to know the V Thevenin's. So we are going to calculate V Thevenin's. We calculated. So that is equal to I Norton's into R Thevenin's. R Thevenin's already we calculated. I Norton's. How we are going to find the R Norton's? Simply short it. AB terminals. Find the what is the current across the AB terminal. Okay. Then what is happening? Here we are going to calculate. So I want the current in this one. Okay. So here how we are going to calculate this one? Simply do this one. Okay. So I want to this one. I reduced the current which is flowing through the current. Okay. From this one I can calculate. So here what is the current here? 10 amperes coming. 10 amps coming. Okay. So here 2 branches. I want to this the current here. Same current is flowing. I want to know the current in the 2 ohms resistance. So branch method I can calculate, that is equal. We can write the IN Norton's. IN is equal to, I want this branch. So what is the total current? 10 amperes into opposite. What is the 3 ohms divided by 3 plus 2. 3 plus 2. So you know the branch current, that's a division branch. So this is the value you are going to calculate. This is the value that what is a 6 amps. Okay, by simplifying, so 5 1s are 5, 5 2s are 2 3s are 6 amps we got it. Now we know the IN, we know the R, then simply substitute this value. So that is equal to, you are going to get it. What is the IN? 6 amperes. What is the R Thevenin's? We got it 5. So that is equal to, we are going to the nearly 30 volts. So here we know the V Thevenin's, we know the R Thevenin's. Simply substitute here. So what is the value here? Or V is equal to, V Thevenin's is equal to 30 whole square divided by 4 into orthogonals. What is the orthogonals? We have got it. So that is called 5. So then we are going to get the nearly, by simplifying this one, we are going to get the 45 watts. So this is a maximum power transmitted from source to load is equal to 45 watts at that condition, maximum power transmission condition. Okay, so this is a one thing you have to remember. Okay, now so this we have calculated. Okay, this is the value we calculated, this value. Now similarly you do the another problem. So let us see, this is a one equation is given where you can see the one voltage source and 10 ohms connected, 20 ohms connected, 25 ohms connected, 5 ohms connected. This is a RL load resistance connected. So this is a variable. Now I want to know that what is the maximum power transmission from source to load this in this case. That purpose I am going to calculate similarly previous case. What to know? I want the R Thevenin's and V Thevenin's I want to know. If you know this value, simply I can calculate the P maximum transmission. Okay. So I am going to give the some hint, you do it. Okay. So here the second figure you can see it. What to do? So here in this case, you first remove this one. Then so we are going to get this equation. 60, 10, this one. I want this is the terminals, this across these two terminals I required. Okay, for this R Thevenin's for purpose, so I will short this value. So I am going to get this circuit. Now I want to know this across these terminals. Now what will happen? So due to this one, so both are the 20 and 10 is parallel and 25 and this is a parallel. Okay. So then I am going to calculate what is the RAB is equal simply 20 into 10 by 20 plus 10. That is the one thing. Next 25 into 5 plus 25 plus 10, that is this one. By simplifying we are going to get this 10.83 we are going to get. Okay. So that is the RAB or we can say R Thevenin's. Okay. After that we find the V Thevenin's. So here what is the V Thevenin's? You are going to calculate. Now I want to know what is the voltage across this one. Okay. So I want to know what is the voltage across this one. So that we are going to get it. So by calculating this one simply, so whatever the equation, just you are going to the voltage and this resistance connected, here is connected the resistance. Now this terminal and this terminal connected, this terminal is connected. This is A, this is B. B. Okay. Then we are going to get the VAB is equal nearly 30 volts we will get. Okay. You know the everyone this one. So you know the V Thevenin's, we know the R Thevenin's. Simply substitute the equation. That is called we are going to get the 20.77 watts. Okay. This is the value, this is the value and we are going to calculate the RL, then find what is the power. So simply we are going to do this value. Okay. Dear students, please practice it. Okay. Similarly, you do the remaining all problems. Okay. What are the applications? It can be used in the stereo cases, in telecommunications, radio transmitters and communication systems we are going to frequently we can use. Okay. These are the some applications of theorem. Okay. Thank you for listening this my class.